Hello friends, welcome to Optical Fiber Communication lecture series. In this tutorial, we'll talk about total internal reflection and critical angle. This is the starting point of understanding the communication in optical fibers using light. So the first thing that we need to understand is the concept of refraction. Whenever there is a boundary between two medium, let us say this is the boundary of the medium, this is eta 1. This medium has refractive index eta 1, this medium has refractive index eta 2, and if we send a ray of light from medium 1, it should not go into this dotted path straight. It will either move towards normal or away from normal. So there is a very famous rule in optics that if we go from denser to rarer, it will go away from normal. So this is what I've shown, that eta 1 is greater than eta 2. So we are going from denser to rarer, so we'll move away from normal. Now what will happen if I increase this incident angle? This is, by the way, incident angle which is made with the normal of the boundary. So what happens if I increase this incident angle? At certain angle, a certain angle theta c, which will be known as the critical angle, this refraction will be large enough that it will make a 90 degrees angle here. So it will not go into the other medium at all. It will stay at the boundary, and beyond the critical angle it will come back, and that is known as total internal reflection. So that is what happens in optical fibers. As you know, in optical fibers there is a core, there is cladding, and we always keep the refractive index of core to be greater than refractive index of cladding, because otherwise total internal reflection would not occur at all in the first place. Because if it starts moving towards normal, then we can never expect it to come back into core, because we eventually want the signal to travel like this, bouncing like this within the core, and that could only happen if eta 1 is greater than eta. To understand this, we need to find out that minimum angle that we must send this light into the core so that it turns back into the core as totally internally reflected ray. So for that we apply Snell's law, where eta 1 sine theta I incident is equal to eta 2 sine theta r. So a little bit of rearrangement, and we need to find this condition where the refraction is 90 degrees. So what happens is we get sine of theta c is equivalent to eta 2 upon eta 1, and this critical angle becomes equivalent to sine inverse of eta 2 upon eta 1. Alright, so this is a very important formula that we need to remember. So let us say we have a case where the core has eta 1 to be equivalent to root 2, and this cladding has an eta 1 of eta 2 of root 1. So we can send this at certain angle 30 degrees, or we need to find out what the critical angle is. So we can find sine inverse 1 upon root 2. So this will be the angle that we must take in order for this light to come back. Otherwise what will happen, if phi c or 30 degrees is greater than phi c, then this light will come back as TIR. Otherwise it will go into cladding. So that was the concept of total internal reflection and critical angle in optical fibers. I hope you liked this quick video. I'll see you around. Bye.